Okay, let's jump right in. If you've ever stared at a gas carrier's cargo data sheet, you've probably felt like you needed a PhD in thermodynamics just to make sense of it, right? I mean, boiling points, vapor pressures, critical temperatures, it is just a massive, intimidating wall of numbers. But here's the absolute secret to this entire explainer. Every single one of those intimidating numbers is really just one physical relationship, just described in different ways. Once you grasp that single relationship, that spec sheet stops being a blur of numbers and becomes a perfectly clear map of exactly how your cargo is going to behave. You're always going to see four main specs out there: boiling point, vapor pressure, critical temperature, and saturation condition. Now, the maritime industry kind of loves to treat these like four completely separate things you have to memorize, but honestly, they're actually just four different labels describing the exact same physical relationship. Section 1. One relationship, four labels. Let's build this from the ground up, starting with what's actually happening inside a sealed cargo tank. Imagine that sealed tank holding a liquefied gas. Inside, the liquid and the vapor are constantly interacting, kind of battling it out, until they find this perfect, steady balance. We call that the saturation condition. And here is the golden rule of cargo control. At this exact condition, temperature and pressure are inextricably locked together. If you raise the temperature, the vapor pressure inside that tank is going up right along with it, automatically, whether you want it to or not. That is exactly why controlling cargo isn't about controlling pressure directly. You control the temperature, and the pressure just naturally follows. Section 2. Plotting the saturation curve. Let's see what happens when we map that locked relationship out visually. When we map out that temperature and pressure dance, we get a unique saturation curve for every single cargo. And suddenly, it makes total sense why different gases demand completely different ships. Take LNG, which is mostly methane. Its curve sits at drastically lower temperatures. We're talking a boiling point around minus 161 degrees Celsius at normal atmospheric pressure. But LPG, like propane, its curve sits much higher, boiling at about minus 43 degrees Celsius. Because methane's curve is stuck in that deep cryogenic zone, LNG literally requires a completely different containment system. You need massive insulation and atmospheric carriage, whereas LPG actually gives you options like pressurized or semi-refrigerated tanks. Section 3. The critical temperature limit. Every single one of these curves eventually hits a point where the rules completely change. Every saturation curve ends abruptly at a hard, undeniable wall. We call this the critical temperature. And the reality of this limit is pretty wild. Above this specific temperature, it is physically impossible for that gas to exist as a liquid. Literally impossible. It does not matter how thick you make the tank or how much immense pressure you pump in. The liquid phase simply vanishes. So let's put that physics rule to the test with a hypothetical scenario. Say a shipping company wanted to save a fortune by ditching those expensive cryogenic cooling plants. Could they just build a massively strong, high-pressure tank and carry LNG at a balmy 0 degrees Celsius? Absolutely not. And one number proves exactly why. Minus 82.6 degrees Celsius. That is methane's critical temperature. 0 degrees is way above that limit. So, because you're past the critical temperature, absolutely no amount of pressure will ever force methane back into a liquid. This right here is why the industry didn't try to engineer around cryogenics to save a buck. They engineered specifically for it. It's the only option physics actually allows. Section 4. The legal 2.8 bar threshold. Let's shift gears from pure physics into the high-stakes world of maritime law. Under the IMO's IGC Code, there's a really strict legal gatekeeper rule. A cargo legally requires a specialized gas carrier if its vapor pressure exceeds 2.8 bar absolute at a reference temperature of 37.8 degrees Celsius. Now, why 37.8 degrees? Because that temperature perfectly represents the absolute worst-case, hottest tropical conditions a ship might face out on the water. If a cargo crosses that 2.8 bar line in that kind of heat, a standard chemical or product tanker is no longer legally or physically safe to hold it. Let's put some real-world numbers to this, just to see how stark that divide really is. Take propane. At 37.8 degrees Celsius, its vapor pressure spikes to nearly 13 bar absolute. That is miles over a 2.8 bar threshold, making it without a doubt a gas carrier cargo. Contrast that with a heavy, low-volatile chemical. At that exact same tropical temperature, it might sit at less than 1 bar. That chemical is well under the threshold, so it can safely travel on a standard liquid tanker. That one single regulatory line dictates the makeup of the entire global shipping fleet. Okay, quick check to make sure we've totally nailed this. Let's say you're looking at a spec sheet for a liquid cargo, and it clearly reads 1.5 bar absolute at 37.8 degrees Celsius. Does international law demand you load this onto a gas carrier? Nope, because it sits at 1.5 bar, which is well below that 2.8 bar gatekeeper. It's just a standard tanker cargo. Keep in mind, just because a substance is quote-unquote liquefied or stored under a little bit of pressure, that doesn't magically make it an IGC-regulated gas. That strict thermodynamic threshold is the ultimate judge. So, pulling it all together, we've walked through a really clear chain reaction in this explainer. We started by seeing how temperature locks to pressure. We mapped that relationship onto a saturation curve that's completely unique to each gas. We found the absolute physical limit of that curve, the critical temperature, and then we applied those pressures to the IMO's 2.8 bar legal threshold, which ultimately decides exactly what type of ship is legally required to carry the load safely. You just connected raw, first principle physics directly to international ship classification. Which brings us to a pretty stark warning for your day-to-day operations. Always, always verify the actual vapor pressure of your cargo. Because think about it, what happens if the loading paperwork is just wrong? What if a batch gets mislabeled or contaminated with a lighter hydrocarbon? If that cargo's actual pressure spikes past the threshold on a ridiculously hot day, you could suddenly be facing IGC level pressures inside a standard hull, and that hull was never designed to hold it. Physics really does not care about your paperwork. So before you close the manifold on your next loading operation, ask yourself, do you truly know what's in the tank?